Alright, so I just finished making the first solution video for the momentum, like the introduction to momentum, and I gave a quick peek to the problems that are on this next set, and they get a bit trickier, so I thought I'd start with an overview. Now, admittedly, I could have done some of this in the previous video, but it really wasn't needed until now. So let me go through this step by step so that you can understand the notation that I'm going to be using. It's a little bit different than Mr. Dawson's notation, which is totally fine. In fact, I'd suggest you just look at both and choose whichever one more naturally clicks with you. But give this notation at least a shot. Okay, so momentum overview. Just a quick reminder. P stands for momentum. We use that extensively in the first worksheet, but new in this worksheet is going to be the concept of impulse. So impulse, the letter that I prefer to use for impulse is J. Now I realize that doesn't really make any sense. I for impulse is clearly more tempting to use, but truthfully, J is a more universal letter used for impulse, and it's just the habit that I have, so I'm going to use J for impulse. It's a little weird at first, but you get used to it real quickly, so give it a try. And of course, in grade 12 physics, capital I will be standing for current, which is usually not a conflict because we're either dealing with circuits or momentum, and rarely do they two come together in the same kind of a problem. But nonetheless, just to give you a heads up, I'm going to be using J for impulse. If you want to use a capital I for impulse, be my guest. Okay, now, the next part, admittedly, is way more important in the world of advanced placement physics, but I am going to use it here. It's going to make a lot of sense when things get trickier, so please bear with me. I know that it's going to be seemingly overcomplicated at first, but in the end, this will be awesome. So I'm going to make a big deal of defining your system in all of these problems, especially if there's something that is not obvious. I mean, if a question just says, there is a car moving on the highway, what is its momentum? You know what? Fine, just go into it. P equals mv, get it done, and go to the next problem. But as soon as there's kind of anything tricky, like two things are interacting with each other, a block hits a cart or something like that, as soon as there's more than one thing especially, it's really important that you define your system. Now, the word system simply means kind of that one or more objects that I am drawing my attention to. So, for example, in some problem, there might be just one ball, and that's really all that's happening. A ball is falling to the earth, or it could even be that a ball hits something like a wall, and I might consider just the ball to be in my system. Even though the wall is interacting with my ball, I might say, no, just the ball. The ball is my system. Everything else that is not in my system is just generically referred to as the environment. As another example, maybe there's two cars that have a collision. So I might declare that I'm going to consider the system of both cars. Notice that I might not include in that system planet Earth or the road or anything like that. I just might say the two cars and nothing but the two cars. Excuse me there. All right, so the reason that this system thing is such a big deal is because it really enables us to make sense of conservation of momentum, especially when we classify forces as being one of two general kind of types. We can define a force as being external if it is due to an interaction of something in my system with something that is not in the system. And of course, the opposite, forces are internal if they're due to one part of the system interacting with another part of the same system, the system that you're considering. This probably doesn't make a whole lot of sense now, but I'm going to be using it consistently throughout this worksheet and the next worksheet. It will start to make sense. Give it a chance. Okay, but maybe just to give you one quick example here, let's suppose that I say a baseball is hit by a baseball bat. If I said, I want my system, sorry, I'm losing my voice here. If I said I want my system to be the ball and nothing but the ball, then the bat would be part of the environment. It would be considered to be able to apply an external force to my ball because the bat's not in the system, just the ball. If, on the other hand, I said, I want my system to be the bat and the ball, then they're both in the system. The ball hitting the bat would be considered to be an internal force. Although, just to be clear, if there was a person holding that bat, and my system was just the bat and the ball, then any force that the person provides to the bat, for example, would be an external force. So you really have to be kind of aware of the system. What is in the system? What's not in the system? Are forces arising due to interactions of things within the system, or things that are interacting from the system with things that are outside of the system? Sounds complicated, but you get the hang of it. Okay, now the reason this is such a big deal is because only external forces can possibly change the overall total momentum of a system. You need an external force, specifically an external impulse. So here is the master equation. Now this is an equation I'm going to be using an awful lot, so let me explain it. I write this as P prime equal to P, notice that there's no little prime, that tick mark, plus the net J external. Okay, so what this says is that the momentum that you end up with, in fact, let me just re-highlight this so I can speak it. The total momentum of your system after something has happened is equal to the total momentum of your system before whatever it has happened, plus allowing for the possibility that there was a transfer of momentum into your system. How do you transfer momentum into your system? Through an external impulse. Now, in case you haven't realized it, this is perfectly analogous to my equation m prime equals m plus the net work nc. So just to remind you of how that worked, this said that the total mechanical energy that you end up with is equal to the total mechanical energy you started with. And how do you transfer mechanical energy? You transfer it with work done by non-conservative forces. Now, I probably should have made it a big deal back in the work energy unit, and maybe next year I will. But to be clear, we were already using the concept of systems back then too. So the mechanical energy of your system is equal to the mechanical energy of your system, right, before and after, plus work that is transferred into your system by things that are external to your system. So we've already been using the system, we just didn't make it as big of a deal as I am now. So going back to momentum, though, it says the same thing. The momentum you end with is equal to the momentum you started with plus the net impulse done to your system or provided to your system. All right, so reminder, though, unlike mechanical energy and work, momentum and impulse are vectors. That's a huge difference between work and energy. So you can do this all in components, for example, x and y. Now, like I said, this probably doesn't make a super lot of sense, but I think it will after we start doing some examples. So I'm going to go right back to the beginning here. This is that second worksheet from the momentum. So let me scroll all the way back. I just did that as a page at the end. Okay, here we go. Let's apply this to see how we can get through these problems. Okay, number one, Charlotte, who's a 65 kilogram diver, shoots a 2 kilogram spear with a speed of that much at a fish that darts away quickly. So I'm trying to just visualize this here. So Charlotte shoots a spear. Now, there's also a fish here, but I don't think that the fish has any real relevance here. So how about if I define my system to be the person, Charlotte, and also in my system I will include the spear. Okay, so both of those things are in my system. The water is not in my system, the fish is not in my system, etc. Okay, just these two single objects, Charlotte and spear, person and spear. Okay, now, presumably, and again, you have to read into these questions a little bit, there's no mention of motion before shooting the spear, so I think that I'm going to assume the simplest possible situation, that Charlotte and the spear were both stationary before she shot the spear. So I'm going to say that let's get this all organized. The mass of Charlotte is 65 kilograms. And I'm going to assume that her velocity initially was 0. So the velocity of Charlotte initial, 0. I'm not using an I for initial, I'm using that prime, no prime notation. So that's the velocity of Charlotte, no prime. Okay, so then there's a spear. So the mass of the spear is 2 kilograms. And again, before it was shot, I'm thinking that the velocity of the spear was 0. Okay, Charlotte moved backwards when the spear is shot. Oh, okay, so then the spear is shot. So the velocity of the spear after it was fired is 15 meters per second. And the question ultimately is, how fast does Charlotte move backwards when the spear is shot? So what is the velocity of Charlotte after the firing of the spear? Okay, now I don't know anything about directionality here, so let's just say that the direction of initial motion for the spear is what I will regard as positive. So whichever way she shot this thing, that's my positive direction. Okay, now, again, don't forget that my system consists of both Charlotte and the sphere. So what I'm going to say is the momentum of my system, Charlotte plus sphere, after has to be equal to the momentum of my system, Charlotte plus sphere, before the firing of the sphere, allowing for the possibility of any net impulse done by external things. Now, I don't think there was any external forces that provided any meaningful impulse here. Presumably there's a downward force of gravity, but that's going to be offset by the fact that she's underwater and is kind of being held up by the water. So vertically, there's really nothing exciting happening. So what I can do is say that there's none of that. It would require an interaction with something outside of the system for there to be an external impulse. And furthermore, a net impulse, right? So there's there could be forces coming from outside the system, but if they all add up to zero, then there's still no net external impulse. Okay. Hey, by the way, before the firing of the sphere, everything was stationary. So that is also zero. So in this particular question, the momentum before was zero, and there was no interaction with anything outside of the system to change that. So I feel very confident that this system is still going to have no momentum. Now, how is that possible? Well, don't forget that there's two things. There's a person, so Charlotte, after, plus the momentum of the sphere, after, have to equal zero. Now, how is it possible for these two things to add up to zero? Simple. One of them is going to be positive and one of them is going to be negative. In fact, if I solve this for Charlotte's momentum after, it is going to be the opposite of the momentum of the sphere after. So, how do you find the momentum of Charlotte? Easy. Mass of Charlotte, velocity of Charlotte after. That's got to be equal to the momentum of the sphere, but the opposite of that. So mass of the sphere times the velocity of the sphere after. So how do we find the velocity of Charlotte after? Velocity of Charlotte after is going to be negative mass of sphere, velocity of sphere after, divided by mass of Charlotte. Which is, I have all of these numbers available to me, so let me get them in here. So Charlotte was 65, the sphere was 2. Okay, so negative 2 times the sphere was fired at, that's the one number I forgot. 15. 15, all of which is over the mass of Charlotte, which was, 65, right? Yeah, okay. 65. So the velocity of Charlotte after, vector notation, is equal to, so let's get this in here, that over that, negative 0.46 rounded off to 2 meters per second. Okay, so since this is the first example of this type, let me just elaborate a little bit. Let's visualize this. So before she fired the sphere, it was basically this. Here was Charlotte just standing still, and let's just visualize the sphere as another little box. So that was the sphere, and they were both stationary, both at rest. So this was initially. So what is the momentum of this system if they're just standing still? Easy. The momentum of the system is 0. Everything's standing still. Then she fires the sphere, and as a result, the sphere goes flying off to the right at some speed that, I'm not going to rework the numbers here, but it's moving off to the right, so clearly it has momentum to the right. But Charlotte is going to recoil going backwards. Now, they were not going to have the same speed, but they will have the same magnitude of momentum. They're in opposite directions, so they will add up to 0. So this thing, if I think of right as positive at least, this has positive momentum, and Charlotte has negative momentum. But nonetheless, the point that I'm trying to establish here is that this system still has 0 total momentum. Guaranteed, because there was no interaction with anything outside of the system to change that fact. That's what it means for momentum to be conserved. Okay, so with that hopefully established, I'm going to try to solve the other problems a little bit more quickly, bearing in mind that you can pause the video as much as you want or rewatch it as needed, and of course ask questions to me or Mr. Dawson to clarify things. Okay, number 2. Sometimes the curiosity, and by the way, I've literally not read these questions yet, so hopefully I won't be caught off guard too much here. Okay, so sometimes the curiosity factor at the scene of a car accident is so great that it actually produces secondary accidents as a result. True. While people watch to see what's going on. If an 800 kilogram sports car slows to 13 meters per second, okay, so we have a car, sports car, check out an accident scene, and a 1200 kilogram truck continues moving at that speed. With what velocity will the two move if they lock bumpers after rear end collision? Okay, so this is a very classic kind of a thing here. Notice that there's a crash of a car and a truck. I'm going to think of that as my system. Okay, so system, the car, and the truck. Now, the reason that is a really smart choice, by the way, is because I have no idea how much force the car exerted on the truck exerted on the car. I don't know. So if I were to try to think of a system of just the car, I would be really lacking information to do anything meaningful. I don't know how hard the truck pushed the car. Okay, but if I think of the system of both of them, then I guarantee myself that the net impulse provided by that interaction, the crash, is something I can safely ignore, at least in terms of conservation of momentum. It was an internal force. It cannot possibly change the momentum of this system of both vehicles. Okay, so, okay, let me get my numbers all straightened up here. Okay, so there's a car and a truck. I'll just refer to them as C and T. So the, and which way is which? Do we remember which way they're going? Let's just say that there's like a forward direction. Okay, so direction of initial motion. They're both going the same way, so I'll just kind of leave it as that. Okay, so the mass of the car was given as 800 kilograms. And it was, it says slowing down to, but I think that what its velocity was earlier on is irrelevant. We're really just considering the impact. So let's think of that as the velocity before the impact. So that's velocity of the car, 13 meters per second. Positive, it's moving forwards. There's a truck. So the mass of the truck is 1,200 kilograms. By the way, just for the record, these numbers, mass of car, mass of truck, are very, very, very low. In fact, I would say unrealistically small, but I'm not criticizing Mr. Dawson. In fact, I'm going to plead guilty to this myself. I often invent numbers that are just a little bit nicer to work with and not necessarily realistic. In fact, cars and trucks have masses much greater than those numbers. Okay, mass of the truck is 1,200 kilograms. The pickup truck behind him continues traveling at 25 meters per second, leading to the impact. Okay, so that was like prior to the impact. So that's the velocity of the truck, 25 meters per second. What happens then is they crash and the two vehicles lock together. Now, locking together means that however fast the car is moving after the impact, the truck is moving just as fast. They move together as one. So let's say that after the collision, the velocity of the car prime is going to be equal to the velocity of the truck prime. They will have the same velocity. And I do tend to get a bit sloppy with my vector notation. I'll try to be good on this, though. Okay, so with that said, I know that there's no external impulse because when that crash happened, there was nothing else interacting. It's not like there was a helicopter pulling them with a cable or something weird like that. There was no external impulse. I have everything within this collision in my system. So check this out. The momentum of this system after the collision better be equal to the momentum of the system before the collision. I always allow for the possibility of a net J, but I'll be really honest with you, in most of the problems we're going to see, because we're going to be careful about our choice of system, we're usually going to design this to be zero. Okay? In fact, with an appropriately chosen system, you can ensure that that's zero. All right. So the mass of the car, velocity of the car prime, plus the mass of the truck, velocity of the truck prime, okay, so that's the momentum of the system after the collision, is equal to the momentum before, right? Mass of car, velocity of car before, plus mass of truck, velocity of truck before. All right. Now, don't forget that we know that the velocity of car prime and velocity of truck prime is the same, so how about if we call this a generic V prime, since it's not unique to either the car nor the truck? So with that said, I can say mass of car velocity prime, just that generic velocity prime, plus the mass of the truck velocity of, actually not truck, prime, that generic velocity, equal to mass of car velocity of car, plus the mass of truck velocity of truck. Now, on the left side, I can factor out that velocity prime, mass of car plus mass of truck, and that's equal to, I didn't change anything on the right side, mass of car, velocity of car, plus mass of truck, velocity of truck. So I can solve for velocity prime, both vehicles, as being the right side, mass of car, velocity of car, plus mass of truck, velocity of truck, all of which is over mass of car plus, mass of truck. There we go. Trying to go fast on this one here. Okay, putting the numbers in. Velocity prime is equal to, and yeah, unfortunately I have to do some scrolling here. So the car was 800, 1200. Okay, so 800 plus 1200. Okay, their velocities before the collision were 13 and 25. 13 and 25. All of which is over 800 plus 1200. All right, so velocity of them combined is going to be, let me just compute this, 800 times 13 plus 1200 times 25, all of which is over 800, well, 2000. There we go, 20.2. meters per second. Okay, now let's just see if this makes a little bit of sense here. So the truck was coming up from behind pretty fast, right? It was coming up, in fact, we've got the numbers here. The truck was coming up 25 meters per second. Bam! Check that out. It does make sense that it's going slower now, right? It was going fast. It rear ends the car in front of it. The truck slows down. Meanwhile, let's look at it from the car's point of view. The car was going 13 meters per second, kind of slower, and then a truck comes from behind, hits their rear end, pushing their car forward. Bam! All of a sudden, they're going forwards faster than they were before. That's basically what happened here, and momentum was conserved. Okay, moving on. Number 3. Okay, Gene rolls a 7-kilogram bowling ball down the alley. Pin standing still, hits it head on. Okay, so there's a ball and a pin with the velocity of that. The pin acquires forward velocity. This is very analogous to the question we just did, and that's not unusual. Like, momentum is almost always kind of the same kind of a situation of collisions and the like. Okay, at least that's where it's really, really effective. So the problems tend to get a bit stale. Okay, I'm just going to call it a person. Actually, no, the person is really irrelevant to this because I'm going to think of just that ball already rolling down the alley. So the person, I don't even need to think about the person. I'm just thinking of a ball and a pin. In fact, let's declare my system to be that. System is the ball and the pin. The person is history, okay? They got the ball going, but that's irrelevant, at least for the physics of this collision. So ball and pin. So the mass of the ball is 7 kilograms, and I'll use that direction of initial motion positive again, so whichever way that ball is moving. In fact, right here, velocity of the ball before the collision is, so the pin, G hits a head on at a velocity of 9. I think that was the velocity of the ball before the collision, 9 meters per second. The 2-kilogram pin, so the mass of the pin is 2 kilograms. Acquires a forward velocity of 14 meters per second. So the velocity of the pin is 14 meters per second. What's the new velocity of the bowling ball? Okay, so the velocity, in fact, I'm being a little bit too fast. This is the velocity of the ball before the collision, 9 meters per second. I'm asked to find what is the velocity of the ball after the collision. And my bad here, I'm going to erase this. I'm going a little bit too fast. The velocity of the pin was actually 0. It was just sitting there until it got hit by the ball. So the velocity of the pin after the collision is, that's the 14 meters per second. It was originally stationary though. So the system is my ball and pin. Notice that there is nothing else interacting with my system. Again, vertically, there's just balance of downward force of gravity and normal force up, so that's completely uninteresting from a point of view of net impulses. So the momentum of my system after is equal to momentum of my system before. I always allow for the possibility. And of course, in maybe later problems, that will start to appear as non-zero, but don't be too surprised if this gets a bit repetitive as being 0 often. But not always. Okay, so let's not forget about its importance, because it will come into play at some point. So there is afterwards, there's a mass of a ball with a velocity of ball prime. There's a mass of a pin, velocity of pin prime. And that's equal to the mass of the ball, velocity of the ball before. Just get these vectors in here. Plus, I'm just going to say 0. The pin was originally stationary, so it had no momentum. Okay, so the ball was, I've got all my numbers on screen here, I think, yeah. So the mass of the ball, I'm trying to solve for the velocity of the ball prime. So how about if I just do this algebraically? On the right side equation, I have mass of ball, v of ball. I'm going to subtract the mass of the pin, velocity of pin prime, and then I'm going to divide this all by mass of ball. That would be solving for velocity of ball prime, which is what I was asked to find. So velocity of ball prime is equal to the mass of the ball, which was given as 7. The velocity of the ball before the collision was 9 meters per second, positive 9, minus the mass of the pin was 2. The velocity of the pin prime was 14, all of which is over the mass of the ball, 7 again. So this will be the velocity of the ball prime. Grab a calculator, here we go, 7 times 9, which is of course that, minus 2 times 14, all of which is over 7, got it. So 5 meters per second, there we go. So the ball has slowed down. In effect, the ball has lost some momentum, but that momentum has been picked up by the pin, so momentum is conserved. That's it for this problem. Oh, by the way, again, I wrote down Mr. Dawson's answers. I should kind of just be double checking myself, so if I screw something up, I can fix it now. So number 3, good. Number 2, good. And number 1, where was my answer? Oh, there it is. Number 1, 4.46. Yeah, that was good. Perfect. Okay, moving on. Number 4. Running at 2 meters per second. Bruce, 45 kilogram quarterback. That's a very small. I'm taking this as like Pee-wee League or something like that. Little kids playing football. Collides with Biff, the 90 kilogram tackle, who is traveling at 7 meters per second in the other direction. Upon collision, Biff travels collision. Okay, so again, pretty standard collision question. So let's do all of the same things. So we've got 2 people. I'll just refer to them by their Bruce and Biff. Oh, Mr. Dawson, why do you do this? Give them different names so that I can use subscripts to represent each person. So you know what? Let's use 1s and 2s. Okay, so Bruce, I'm just going to think of Bruce as number 1, like the first person. And the other person I'll just think of as number 2. Okay, so running at 2 meters per second. Okay, so M1 is 45 kilograms. And he was running at V1 equal to 2 meters per second. Now, I guess I should preface this by saying my system is both people. System of both 1 and 2. And I will use the direction initial motion, oh, my pen is not working, it's kind of flaking out here. Computer is stalled. Oh, there we go, I think I'm back. Okay, let me get that, there we go. So the direction of initial motion for number 1 is positive. Okay, so whichever way Bruce was running, that's my positive direction. So M1, 45 kilograms, V1 is 2 meters per second, looks good, collides with Biff. So M2 is 90 kilograms, who's traveling at 7 meters per second in the other direction. Okay, so V2 is negative 7 meters per second, just the way I chose to define my directions. Upon collisions, Biff, so that was number 2, continues to travel forward at 1 meter per second. So the velocity of 2 prime continues to travel in the same direction he already was. So that is my negative direction. Even though it says forward, remember that's forward for that person. It's actually the other way for person number 1. So that is going to be negative 1 meter per second. Vectors for all those. How fast is Bruce knocked backwards? So V1 prime is what we're looking for. This is exactly the same as the bowling question that we just looked at. So I'm going to do this really quickly here. P prime equals P plus, there was no net J, because I've, again, designed my system to be that way. So let's do this. M1V1 prime plus M2V2 prime equal to M1V1 plus M2V2 vectors for everybody, all the velocities. We're looking for V2 prime? V1 prime. Okay, so solving this for V1 prime, the right side doesn't change, M1V1 plus M2V2. I then subtract M2V2 prime and divide the whole thing by M1. That would solve for V1 prime. Okay, putting my numbers in, V1 prime is equal to M1 was 45, V1 was, I have to peek there too, plus M2 was 90, V2 original was -7, minus M2 was 90, V2 prime was -1. And don't lose track of these negatives. Like, this is really, really important. All of which is over M145. Okay, so grab a calculator. Numerator is 45 times 2 plus 90 times 7, -7, and then subtract -90 times -1. Okay, so there we go. All of which is over 45. -10. So V1 prime is -10 meters per second, just like that. Did I agree with Mr. Dawson's answer? He says +10. Well, of course, depending on how you set up your directionality, it could be either way. Or you could think of it as how fast is Bruce knocked backwards. You could just think of that as a speed if you wanted to and report it as positive either way. But you know what? It doesn't really matter to me right now. I've got the velocity, including a direction. So I think +10, -10, as long as you have the support around it to explain what you're doing, I'd be happy with it. So I'm going to press ahead. I'm trying to get these done as quickly as I can. Number 5. To test the strength of a retainment wall designed to protect a reactor, a rocket-propelled jet aircraft was crashed head-on into a concrete barrier at high speed. The Phantom had a mass of that much, while the retainment wall's mass was really big. The wall sat on a cushion of air that allowed it to move during impact. So essentially there's no friction or anything like that. If the wall and the F4 move together at that speed during the collision, I think that probably means like after the collision, what was the speed of the Phantom upon impact? All right, so there was a jet and a wall. So let's define our system to be both so that we can take advantage of that awesomeness of a zero net impulse. So system of jet and the wall. Okay, and I'll use direction of initial motion positive for the jet. So, getting the numbers in here, the jet had a mass of that. Okay, mass of the jet is 19,100 kilograms. And the wall has a mass of a lot more than that. The mass of the wall is 469,000 kilograms. Okay, they move together. Okay, so the velocity of the jet after is equal to the velocity of the wall after, let's call that a generic velocity after, of 8.41 meters per second. And it says during the collision, but I think that means like right after the collision. So the question is, what was the speed of the jet prior to impact, like just upon arriving there? So the velocity of the jet is what we're looking for. And a quick little tidy up for my vector notation should be good. So this time it's the initial velocity that we don't know. Big deal. It's all good. P prime equals P plus the net J, and of course vectors for everybody, but none of that. So the after collision is the mass of the jet moving at a velocity of jet prime plus the mass of the wall, velocity of the wall prime, equal to the mass of the jet, velocity of the jet, plus the wall was initially stationary. Okay, they both had the common velocity afterwards, so why don't we refer to that generic v prime. So mass of the wall, v prime, equal to the mass of the jet, velocity of the jet. Now, since they had a common velocity, I can just factor that out. This is completely optional, but kind of nice. Mass of the jet plus the mass of the wall. And if I divide all of that by the mass of the jet, I will get the velocity of the jet. That means the velocity of the jet can be found. Oh, we have vectors for everybody. Yeah, truth be told, I often don't bother, but like I said, I'll try to be good with vector notation on this one because it's super duper important. Okay, so velocity of jet is equal to, okay, so what I need is the v prime of 8.41, 8.41, the combined mass, so the jet plus the wall, so 19100, plus the wall was 469,000, 469,123, all of which is over the mass of the jet only, which is 191,000. And that should do. The velocity of the jet, this is just prior to impact, is 8.41, 191 plus 469, and I'm getting all those zeros in there, divided by 191. So I'm getting 2 rounded off to 15. 215 meters per second for the velocity of the jet just before it hit the wall. Just double checking with Mr. Dawson there. Perfect, we agree exactly. Awesome. Moving on. Number 6. Valentina, the Russian cosmonaut, goes outside the ship for a spacewalk. Very timely, right, with the recent news of the rocket launch. But when she's floating around 15 meters from the ship, her tether catches on a sharp piece of metal and is severed. Oh no, this is catastrophic potentially, but fortunately I think Valentina knows physics and she's going to save herself. So Valentina tosses her 2-kilogram camera. No, not the camera. Surely she had something else she could have thrown. Away from the spaceship with the speed of that. How fast will Valentina, whose mass is that, travel towards the spaceship? And then part B, assuming everything's at rest in that frame of reference, how long will it take to reach the ship? Okay, so even though things are moving like in orbit, etc., I think all of that is basically irrelevant. We can treat everything as being essentially stationary at the start. So I'm just going to call Valentina the cosmonaut a person, and I've got the camera. So the system of the person and the camera. Okay, now which way is which? I'm going to say the person is going to start moving one way. Of course, the camera goes the other way. So what if I say the direction of initial motion for the person will be positive? So that means the camera is essentially going in the negative direction and the person is going in the positive direction after she throws the camera. Okay, so the mass, let's get all these numbers in here. The mass of the person is, where was it? I thought I had it in there. Oh yeah, it's there, 68 kilograms. And it says mass is now, I think it says mass is now 68 kilograms. This is meant to be the person plus her equipment and spacesuit and all that stuff, but not including the camera. She's already tossed that. So mass of the person, 68 kilograms. The velocity of the person was 0, okay? So we're considering her to have been stationary before throwing the camera. Of course, velocity of the person after she throws the camera is what we're very interested in right away. The mass of the camera was 2 kilograms, and the velocity of the camera was also 0, but then she threw it in the direction that I'm considering to be negative, so 12 meters per second. Now, again, I've chosen the system. There's no external impulses, so this is going to be nice and clean. P prime equals P, plus there is definitely no net J. Like I said, don't be surprised if that's 0 most of the time, but that's because we're like cleverly kind of rigging our equation to be that way. That is the awesomeness of this approach. And yet I'm writing it every single time because eventually we're going to come across situations in which it is not going to be 0. They're coming, I'm sure of it. So P prime equals P plus the net J. So after this, there is a person and a camera. They're both moving. So mass of the person, velocity of the person, prime, plus the mass of the camera, velocity of camera, prime, equal to the mass of the... Well, actually, before she threw the camera, let's just save myself the step. Everything was stationary. So the person was stationary, the camera was stationary, the system had no momentum. and then they kind of went off. This is going back to kind of like the question with the diver and the spear gun, right? They were stationary, she fired the spear, and the person went the other way. This is very analogous to that. So if you want the velocity of the person prime, simply subtract mass of camera, velocity of camera to the other side, and then divide by the mass of the person. All right, so the mass of the camera is 2. Velocity of camera prime is negative 12. There is a negative up front here that I forgot to write in. Divided by the mass of the person, 68. Now this is going to turn out to be positive, which is awesome, because I kind of designed it that way. I set that to be positive, so it better work out to be positive. So negative 2 times negative 12 is positive 24 over 68 is 0.35. Now normally I would just round this off to 3 figures. How about if I record 5 figures, because I know there's a part B coming up. So 0.35294 meters per second. I'm going to use that later. But as far as part A is concerned, I will report a value of 353 meters per second. So I'm going to call this my reported value, but I'm keeping those extra digits for part B. Okay, and speaking of part B, it asks us now, how long does it take her to get there, right? So, assuming the spaceship remains at rest, and we were told that it is 15 meters away. Okay, so realistically, that just means she's going to go a distance of 15 meters, and she's traveling at a speed, actually, velocity, vectors. Oh yeah, I said I was going to be good about that, didn't I? V prime, there we go. That, one more. Oh, geez, they're like flies. They're just popping up everywhere. Okay, so in fact, here, if you really want to be good about it, that's a displacement in that same positive direction. But she's moving that way. So 0.35294. There's my extra sig figs. And there's no acceleration. She's just going to be cruising along with no forces, no external force, no net force. It's constant velocity. So how long will that take? Just moving that displacement at that velocity? Simple. Velocity is displacement over delta t. So the delta t is the displacement divided by the velocity. So that is 15 over 0.35294. And 15 divided by that is 42.5 seconds. All right, so 42.5 seconds. Do we agree with Mr. Dawson? Yes, we do for both A and B. Whew, 3 more to go. Number 7. A 620 kilogram moose stands in the middle of the railroad tracks, frozen. Oh no, this is not looking good. Frozen by the lights of an oncoming, oh no, locomotive that is traveling at 10 meters per second. The engineer sees the moose but is unable to stop the train. Yeah, trains are hard to stop in time, and the moose rides down the track sitting on the cowcatcher. Okay, so the cowcatcher, there's a footnote here. I didn't read it, but I saw something. Cowcatcher is designed to catch instead of splatter cows. It also works for, so good thing this moose is safe and sound here, having just been struck by a train. Okay, so the engineer sees the moose, blah, 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 blah. What's the new combined velocity of the locomotive and the moose? Okay, well, it's, yeah. Okay, these numbers, just again, I can't help but point this out. A real train, especially like full-on train, like not just one car or something like that, is way, 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 way more than 10,000 kilograms. But hey, nice simple numbers. Because realistically, like for a full-on train, I don't care. I know that a moose is a big animal, but compared to a train, a moose is like, it's like hitting a fly. So realistically, if a real train hit a moose, the train would only slow down imperceptibly. Like it wouldn't really be a concern to the train. It would be a big concern for the moose, but because this is kind of an artificially low number, I think we're going to see some meaningful change, even if somewhat small still. Okay, so let's get to work here. So system, again, of both the train and the moose. Direction of initial motion is positive. The train's motion is forward. Let's just think of that as. So the mass of the moose is 620 kilograms, and it was standing still. Velocity of the moose was 0. Then the train has a mass of 10,000 kilograms. The velocity of the train before it hit the moose was 10 meters per second. And it doesn't explicitly say it, but it kind of does. Combined velocity. So the velocity of the moose after is a generic v prime. The velocity of the train is a generic velocity, since they will move together. Okay, got all those vectors. There we go. So, again, this is starting to be very repetitive, right? Which is fine. It's the whole point of a worksheet, is to kind of get to that point of things are making a lot of sense. So my system p prime is equal to p plus the net, that's a vector symbol, net j, but there was none of that. Okay, there we go. P prime is going to be mass of the train, moving at that common v prime, I'm just jumping to that, plus the mass of the moose, common velocity, equal to the mass of the train, velocity of train, plus nothing because the moose was originally stationary, frozen in fear, I believe it was. Okay, I can factor out that v prime, mass of the train plus the mass of the moose, equal to the mass of the train, velocity of the train. Velocity vectors, there we go, got them all. That means the velocity prime, this common velocity, is equal to the momentum of the train, mtvt, divided by their combined mass, so mass of the train and the mass of the moose. V prime equal to, so this is the thing I was set out to, or asked to find, mass of the train, 10,000. Velocity was moving at, I think, 10. All of which is over the mass of the train again, 10,000, but this time adding in that little extra for the moose, which was 620. Okay, so getting an answer out of this is just 100,000 divided by 10, 620. And that gets me 9.42 rounded off to three figures. 9.42 meters per second. There we go. Do we agree with Mr. Dawson? Yes, we do. Awesome. Moving on, number 8. D is rolling along on her 4 kilogram skateboard. So there's a person and a skateboard with a constant speed of that. When she jumps off the back and continues forward with the velocity of that relative to the ground. This caused the skateboard to go flying at the speed of that relative to the ground. What is D's mass? So again, there's a person and a skateboard. If I put them both in the system, then however they interact with each other will not be of any consequence to the system momentum, rather. And because the skateboard rolls beautifully on wheels, effectively there's no friction and all that stuff. So really it's going to be one of those beautiful situations of no net impulse for this system. So system is the person and the skateboard. And we'll again use the direction of initial motion positive. Okay, so routine. P prime equals P plus the net J. Honestly, I think for the next worksheet I'm going to give up and stop writing in vector symbols. They are vectors. As long as you're counting for direction, I'm usually happy to be a bit lazy with that notation. But I'll stick with it for the rest of this worksheet. So P prime equals P plus the net J. So afterwards there is a, in fact, let me just make sure I got this right. So she's on the skateboard, constant speed of that. Oh, let me write that out, in fact. Mass of the skateboard is 4 kilograms. The velocity of the skateboard and the person were both the same, actually, originally, at 3 meters per second. Then she jumps off the back and continues moving forward. Okay, so still positive. So the velocity of the person after jumping off is 2 meters per second. This caused the skateboard to go flying with the speed of that. So the velocity of the skateboard after, 15.5 meters per second. What is the mass of the person? So mass of the person is the unknown. So same kind of routine, different unknown. Okay, so mass of the person, v of the person prime, plus the mass of the skateboard, velocity of the person, skateboard. Skateboard prime equal to the mass of the person, v of person, plus the velocity, mass of the skateboard, velocity of skateboard, original. Okay, solving this for mass of person is the right side of the equation, mpvp plus msvs, subtract mass of skateboard, velocity of skateboard prime, all of which is over the velocity of the person prime. Yeah. Oh man, all these vector symbols, right? So all of these get vector symbols. There they go. So mass of the person is equal to, get the numbers in here. Oh wait, did I screw something up? Mass of person, oh gee, okay. This is me just going a little bit too fast. I'm trying to solve for mass of the person, but it's in two terms. So I haven't really made an algebraic mistake, but it's not a good way to do it. So let me back up. Yeah, mass of person is spread across the equation, so we're gonna have to get those together. Okay, in fact, let's just take it all the way to here. So because mass of the person is in two places, again, that's just something that I wasn't being careful enough with, we're going to put them the terms both on the same side of the equation. So let's leave MPVP prime right where it is. Let's subtract that other term from the other side of the equation to join it. Mass of person, V of person. Okay, so there it is. Now on the right side of the equation, there already was an MSVS. And let's subtract that other term here, like let's subtract that over to join it. So mass of S, V of S prime. Perfect. Now that the mass of the person is kind of together on the one side of the equation, I can factor it out. So mass of the person times VP prime minus VP original is equal to MSVS minus MSVS prime. Now I can solve for MP as being the same thing, MSVS minus MSVS prime, all of which is over VP prime plus, minus VP. There we go. Mass of the person is equal to mass of the skateboard, which was, what, 2 or something like that? Nope, 4. 4 times the velocity of the skateboard, which was originally 3. They were both moving at 3, in fact. Minus the mass of the skateboard, 4 again. Velocity of the skateboard prime, 15.5. All of which is over VP prime, 2, minus VP original, 3. Okay, so mass of the person is equal to, grab a calculator, numerator is 12 minus 4 times 15.5, dividing that by -1. So I get positive 50 kilograms. Phew, glad it's positive, because otherwise I would have been certain to have made a mistake. So 50 kilograms, do we agree with Mr. Dawson? Yes, we do. Good. Moving on. Last problem. So, motorboat turned off as it approaches the dock, and it coasts towards the dock at 0.5 meters per second. Person, mass is that, jumps off the front of the boat with the speed of that relative to the boat. Ooh. Okay, what is the velocity of the boat after Isaac jumps? So I'm going to have to interpret that as 3 meters per second, like relative to what the boat was doing prior to him jumping off. So there's a little bit of kind of a frame of reference thing in here, which we do a big deal of in the AP physics. So I'm just going to kind of sneak this in here and try to not make too big of a deal of it here in 30S physics. Okay, so let's just get into it. So the system is the boat and the person. Okay, the direction of initial motion positive again, should all be clear. Mass of the boat is 300 kilograms, and it is coasting along at a velocity of the boat 0.5 meters per second before the person jumps off. The mass of the person is 62 kilograms. Now, the person was on the boat before jumping off, so they were moving together at the same 0.5 meters per second. Okay, now, the only slightly tricky part here is this jumping off at 3 meters per second relative to the boat. I think I really have to interpret that as relative to the way the boat was moving before jumping off of it. There's a little bit of ambiguity there because the boat's velocity is going to change. So I think that it was relative to the boat's initial motion. I have no choice but to assume that. At least that's what I'm going to choose. So with that in mind, I'm going to say the velocity of the person after jumping off the boat is 3 meters per second plus the extra half meter per second that they had because of moving with the boat previously. So hopefully this is not too much of a stretch to just say 3.5 meters per second. So again, the reason for that 3.5 and not just 3 is because the person jumped off of the boat, but the boat was already moving. And since the person jumped off the front of the boat, essentially moving forwards, the velocity of the boat essentially added on to their jumping velocity. Again, in AP Physics, we make a way bigger deal of this, so hopefully that's adequate for right now. And of course, the question is, what's the velocity of the boat after the person jumps off? So VB prime is what we're looking for. Okay, system P prime equals P plus, we've designed it, that there's no net J. Okay, so it didn't show up in this worksheet at all, so it probably will in the next worksheet, that there will be non-zero net J, I hope. Otherwise, you're going to think that I'm losing it for writing this every single time and crossing it out. So P prime is mass of the boat prime plus the mass of the person. V of the person prime. Mass of the boat, V of the boat, plus the mass of the person, V of the person, before. So if you want VP prime, and this is straightforward, it's just in the one place. So VP prime equal to M boat V boat plus M person V person, subtract mass of, I screwed up. I just realized I missed the velocity of the person right in here, prime. Yeah, mass of boat, V of boat. Oh, that's what okay. I just missed that. Okay, so let me go back and fix that. That was the mass, pen, go back to pen. There we go. Mass of the boat, make sure that looks better. Boat, V of the boat prime, plus all that other stuff. Good, because that's where I'm at right now. Subtracting that term over. So mass of boat, V of boat prime, all of which is over mass of the person. V of person prime equal to, putting the numbers in, mass of boat was, there it is, 300. The velocity of the boat before was half of a meter per second. The mass of the person was 62. They were also moving at 0.5. But then mass of boat is 300. Wait, did I screw that up? We're trying to solve for V boat prime. Ah, nuts. Okay, so let's just make this quick. It's the V of the boat prime that we're trying to solve. So I'll just do that. And since they were literally in the same points in the equation, I can just switch this to mass of person, V of person. Yeah, I somehow botched that up. So I think that I'm back on track here. So minus the mass of the person. This is what happens when you try to go fast. You make mistakes. 62 times the V of the person originally. Prime, right? I'm subtracting that over to the other side here. So V of person prime, which is 3.5. 3.5, all of which is over the mass of the person, which was 62. And, you know what? I said I was going to get lazy not until next time. I think I'm officially lazy now. I'm not going to bother putting the vector notation in. You guys get it, I'm sure. So, numerator, 300 times 0.5 plus 62 times 0.5 minus 62 times 3.5, all of which is over 62, which is V of boat prime is negative. Okay, so negative means that the boat is going opposite of that initial motion. So the boat, not only did it like slow to a stop, it's actually going like quote backwards now. 0.581 rounded off to 3 figures. Okay, and since I'm getting a bit sloppy here, I'm really hoping to agree with Mr. Dawson, and of course, no, I don't. Nuts. And I'll almost certainly take the blame on that because I got a bit wonky there. So I definitely have a mistake here. Let me just do a quick hunt to find it. Okay, so mass of the boat 300, 62, they're moving together at 0.5, person jumps forwards at 3.5. I think that's all good. Okay, I probably screwed up this algebra somewhere since I was going so fast. mass of, okay, so I'm just kind of checking it over. Mass B VB prime plus mass person V person prime. Looks good. Mass of boat velocity boat, mass of person velocity boat. Okay, that all looks good. Okay, then I tried to solve this for V boat prime. Okay, so this might be where my mistake is. M B V B. Okay, so that looks good. Plus M person V person. Good. I then subtracted this term to the right side. So M person V person prime. Now it looks good. All of which is over to solve it for the velocity of the boat prime. Yeah. There's my mistake. Okay. Again, haste makes waste here. Trying to go fast. So just to be clear, my mistake is right here. Hopefully you caught it before I did. In trying to solve for V of the boat prime, it was really supposed to be a division of mass of boat. And I know exactly when I made that mistake, because if you recall, I think I was solving for the wrong variable, and I forgot to update everything. So that mass of P really is supposed to be a mass of B. So let's fix that right now. I will just kind of make sure that that's clear. So this is mass of the boat. There we go. And that 62 really should have been the boat's mass of 300. 300. Okay, that's going to change my answer, hopefully to an agreement with Mr. Dawson. Okay, grab that calculator. I'm just going to go back and change that 62 to 300 because everything else should be okay. So now I'm getting still not in agreement. Well, let me retype it. 300 times 0.5 plus 62 times 0.5 minus 62 times 3.5, all of which is over 300. Oh yeah, there we go. Negative 0.12, which is, I can see Mr. Dawson's answer as well. So yay. Negative 0.12 meters per second, the velocity of the boat after the person jumps off. And it is negative, so what I said earlier does stand. The boat actually recoiled. It's not moving in the same direction it used to be. It's actually going the other way. Phew! Okay, so there we go. I am going to wrap this video up because there is one more I'm going to do very soon. So see you again in just a little bit.